Hello, I'm Jenny Grosslight with Keysight Technologies. This video covers tuning a U4164A logic analyzer-based solution for DDR5 UDIMM debug and analysis. This slide shows the complete solution to be able to capture all of the address command and data off of both of the DDR5 subchannels on a single UDIMM simultaneously. You need the B4661A memory analysis software with the DDR5 analysis option, an M9505A chassis, quantity 4 of the U4164A modules. They each need the U4164A O2G speed option, and they will be configured as two sets of 2 modules each. We recommend an embedded controller. The FS2601 DDR5 UDIMM interposer connects into the socket on the DDR5 UDIMM target and routes the signals from the interposer into the U4164A modules with direct connect cabling. For this demonstration, the DDR5 UDIMM system was operating in 2N mode. Always download the latest U41A and B4661A software from the Keysight website. This will get you the latest enhancements. Before you install the software, remember that administrator privileges are required to properly install the software.
Install the logic analyzer software first and then the B4661A. Once the software is installed, you'll see the icons for the logic analyzer and DDR Setup Assistant on your screen. Double-click on the DDR Setup Assistant icon. This will start a logic analyzer session, and it will also start DDR Setup Assistant. If you have a logic analyzer session already started, DDR Setup Assistant will make modifications to that logic analyzer session. DDR Setup Assistant is semi-automated, and you simply step through the questions. In this example, we're using DDR5. We are using the FS2601 UDIMM interposer from Future Plus Systems. On the DDR5 DIMM, there are 2 channels. There's subchannel A and subchannel B. With this particular system, we only have a single module, so we're going to load just channel A, and in fact, with only one module, we're only going to see the command address and 1 byte line of data. When we check the software installation, this is going to make sure that you have licenses available for the different technologies. You only need the licenses for the technologies you're interested in. Now here, we will load the standard configuration. That's typically what you want to do. DDR Setup Assistant loads the configuration for us. The default configurations are very important because they contain all of the labels that the software analysis tools require and that DDR Eye Scan requires for you to properly tune your system. So that's loaded it for us. On the hardware setup, that help will tell you a couple ways to find the latencies on your system for read latency and write latency if you don't already know them. The hardware setup step is a document that tells you how to look at your probe tool and see how to connect your signals. Rather than look at the help document here, why don't I show you what it would do? We have to cancel the lock that DDR Setup Assistant puts on. We go to the overview. In the overview, the default configuration will have a probe connection tool. We can look in the probe connection tool, or you can look in the user guide that comes with your interposer. It's going to show how you connect the pods from the interposer to the logic analyzer. Very helpful, and also when it's in this state, it will tell you which of your modules you're actually connected to. If you were offline, the module might not correlate correctly. So now we go back to Setup Assistant. The step's complete. We have our hardware connected. We set the initial thresholds. Step complete. We find the clock and chip select settings. And you notice it may take a minute, depending on how much traffic you have. It says that it found them, except it didn't find any for chip select 1. I expect that because this is a single rank system, so there's not 2 chip selects, just chip select 0. Step complete. So since I only have a single rank system, it's going to be just chip select 0 that I select in the next step, where we're going to find the command address sample positions. Now this is important because you've got to let the system know which chip selects are valid. Again, what Setup Assistant is doing in the background, it's already found the correct threshold looking at the signal swing. Now it's looking for the correct sample positions for each of the CA signals. Step complete. Here, the latency, I know that this system is 38 for the read and 36 for the write. It's actually operating right now at DDR5 3200. We apply those latencies. That step's complete. That step puts those latencies in multiple tools for you so that the tuning is appropriate to find best sample position for the data, and that's related to the read and write latencies, because we need two different sample positions, one for the read and one for the write. And actually, since we're sampling at such high data rates on DDR5, we're finding a sample position for data read rising and a sample position for data read falling, and then a sample position for data write rising, and another one for data write falling. And the logic analyzer internally has circuitry that lets it have just one signal in from the probe point, and it gives the internal acquisition in the logic analyzer 4 samples from that. The first thing we want to do is go ahead and let the system find the ideal threshold, find the data read sample positions, and this can take a few minutes, depending on how much traffic you have running. The more traffic you have running, and the more random the traffic, because that's the most challenging condition for the bus. The eyes will be the smallest when there's random traffic and lots of it. So when you're tuning under those conditions, you'll be tuning under the worst case conditions and thereby setting the best sample position. DDR Setup Assistant completed. There are warnings because we're not using the check bits. Next, we would do the write sample positions. DDR Setup Assistant finished and did have some warnings. These are signals that this system is not using. At this point, it's a good idea to go back and double check the sample positions that have been set before we go into determining the best sample position with the final read scan and final write scan. We go back to the logic analyzer and cancel the log. Open up the sampling tab and go into Eye Scan. For the clock, the first eye to the left of 0 is the appropriate position, and we see DDR Setup Assistant has gotten the appropriate sample position. Chip select will be in the first eye to the left of 0, and here we notice that only chip select 0 is active, and that's because we have a single rank system. Command and address will also be in the first eye to the left of 0. All of them look good. Read data, we need to open up the composite and look at each of I'll show you what it did. It went in and actually changed to signal trace mode and did do not store back-to-back memory bursts. This gives it the start of the burst because there's no back-to-back. We get to see a clear beginning of the burst, and then we can put all of the rising samples in the first sample of the burst, and the falling will go in the second sample of the burst. That's because we're capturing the rising and falling on the same clock edge and using 2 samples to capture rising and falling simultaneously, and the software stitches the results back together for the analysis. We had similar on the data write rising and data write falling, although here it looks like DDR Setup Assistant put us in not the first eye for the rising, so we want to move them to the first eye. And here I can right click to set to suggested, but I have to unlock it, and we'll set just the sample position to the suggested. On the falling, we want it to be in the second eye. So I'll move the composite over, get them all in that second eye, and then just set the sample position to suggested, and they'll pop to the best position in the eye. If we want to be able to see that a little better, we can go in here and reduce the range. I can go to actually 1.5 would get near the beginning of the burst. And since they all cut off by about 2.4, this gets us, I wanted -1.5. nanoseconds to 2.4 nanoseconds. We still get to see the beginning of the burst, but the eyes are a little bigger for us. Now, we should lock the sample positions once we've got them, just so nothing gets changed. Once DDR Setup Assistant has found the best eye in the burst, and you see that there actually are open eyes for more of the burst, then we can go back into Setup Assistant and let it complete the tuning by doing the final read scan. When it goes in this mode, it's going to overlay all of the eyes in the burst. So we want to be locked in that sample. Click OK, and we'll do it for the rights also. Click OK again. At this point, we've done as much as we can with DDR Setup Assistant. It's completely tuned the system. Notice we're in the reads, but now the reason we have that signal trace mode is to find the first eye in the burst. Because looking at this when it's in the overlay mode, you couldn't determine which eye to set the sample position in to know which one would be the first. Now it's overlapping all of the eyes. Let's look at what it's doing. In the scan qualification, what it's set up in this mode is it went into eye overlay mode, and it's going to capture and store all memory bursts. It doesn't care if it's back to back or not. So it ran faster and actually just caught them all. And we see we actually have a nice big open eye when the system is running at 3200. As it goes faster, these eyes are going to get smaller and more challenging. So next, we'll go through changes manually in DDR Eye Scan. We'll do manual changes to DDR Eye Scan so that we can scan the full eyes and distinguish the best sample position. And again, on the rights, we had it locked, so these are the appropriate eyes, and we did find overlapping eyes on all of the signals. We click OK. Now when we take a trace, we make sure we're configured correctly and compute. Here, we're capturing tuned DDR5 traffic. We can see the clock frequency at 1.6 gigahertz for the 3200 data rate. If we're on one of the reads or writes, and we go to the details, when we click on one of the reads or writes, let's go into say the fourth one, and we click on the details for that, we get the activate, the read that we're on any other reads or writes on that open page, and the pre-charge that closes the page, and we get all of the data that was sent on that particular read. I can go down and look at the next read, and I get the data sent on each subsequent read to that open page. Likewise, we can go in and look at our writes. And if you're sending a known data pattern, then you'd be able to verify that that was the pattern you were expecting. Let's go back into Eye Scan and run full eye scans now. For the clocks, we won't do that because the clock is our reference and it only runs in iFinder. But for all of the other signals, we can do and show a full eye scan. And what this gives us is what we refer to as signal integrity insight at a glance. You're getting to see all of the signals relative to the clock and to each other scanned by the logic analyzer. If it comes in small like this, just do a simple auto scale this signal. Again, we expected at 0 and it was already locked there. We have different displays that we can look at. That was intensity. We can also go to continuous hue. Some of the different colors are easier to see than others. When you're doing the full scan, you can expand it because it's a Windows view. And now let's go ahead and do the full eye of all of them. Now there is a more advanced mode where you can do a higher resolution. It just takes a little longer. If I want better resolution or zoomed in, I can go say -2, 2 plus 2, or +1 even. And we don't have to spend as much time scanning that. Run this measurement. Here we've got to move the eyes into, we'll select color graded. I need to make sure that we're in the correct eye, which should be the first eye left of 0, or the eye right at 0 sometimes. If there's an eye at 0, it's usually that eye. If there's a crossover right at 0, then it's typically the first eye to the left of 0. Let's go down and make sure they're all good. Let's set them all to suggested. And when we say set to suggested, iFinder is saying, given the eye that it sees, the algorithm selects what should be the center of that eye. We go ahead and lock. These are nice, clean eyes. Now, for the read eyes, in this case, we've already reduced the range perhaps a bit much. So I'll go in and give it a little bit more time on the beginning and make sure that in the scan qualification that I want to be running do not store back-to-back and signal trace mode. Now we're able to see the entire eye with the eye scan. We also get to see the beginning of the burst because it's been scan qualified to not show the back-to-backs. We know we have a real clean start to the trace. We'll go ahead and change that display to the color graded, which lets us see the density a little clearer. We also don't have to show the time-only scan, which is what we refer to as iFinder, or you can leave it in. So what that is if you would say we uncheck the lock here, notice that the iFinder shown below tracks what the eye looks like at the threshold we're at. And you definitely can see where the eye is wider at different thresholds. Go ahead and lock that again and maybe not show those anymore. Now for the final eye scan, we'll actually overlay all of them and it will close up quite a bit, but will be locked. And we do the same thing for the data write. And we notice that we do still have open eyes, even though it overlaid all eyes in the burst. This is excellent. So we'll have good eye position, eye sampling for the data. We might want to go in and adjust for the best sample position in the overlaid eye. And again, we could do that rather simply by going to the composite, right click and set to suggested. And it'll pop all of them to their suggested eye. Might want to adjust it, but you're good to go. And you have some signal integrity insight to see if one eye is closing relative to another, if there's any reflections, which are typically show as on the rising and falling edge. And we can make sure that we have the falling in also. Now they're really the same eye, right? The rising and falling, we're just capturing them at a different sample point because the logic analyzer split the one probe point results into 4 and sent it into 4 locations in the acquisition. With that, we're fully tuned and have the full eye scans and can capture the most accurate state mode traces for memory analysis possible.